In this video, we'll talk about some examples of systems differential equations and why they might be important and relevant going forward. So the first example here is a bioreactor. So we consider a bioreactor described by the following equations. We have dx1 dt is mu minus d times x1, and dx2 dt is d times x2f minus x2, or whatever those values are, minus mu x1 over gamma, where x1 and x2 are the biomass and substrate concentrations in the reactor. So those are the two things that are changing over time. And the growth at mu depends on the amount of substrate given by the formula here. So the point is, in this sort of reactor, we have two different things that are changing. We have the biomass, the mass of the organism that is actually doing the reaction, and the substrate that we're adding to do this reaction to make this happen. And so processes from chemical engineering or biomedical engineering would develop these equations for the system to know how exactly mu relates to x2, how the growth rate's going to affect how things work, and how it all comes together. The question you could be asked in a future class like that is integrate the system over time to obtain concentration profiles given certain values of the parameters. So if I tell you what is this mu max for in here, what is Km, what is K1, what is gamma, x2f, and d, you can then take that information and see what's going to happen over time to this system. All right, we could run this data using a numerical model, try to figure out what's going to happen over time and what we're going to get out of the reactor as time goes on. We can usually do so for different conditions, so different starting values for the biomass and the substrate, and see what happens over time. So these systems are really useful because they can model situations where multiple things are changing, and we can use them to analyze more complicated behavior than we could before with just one thing changing in time. We can now analyze multiple as well and analyze more complicated systems with it. Also gets to the idea of numerical models being used for these as well. There's our first example. In our second, we now have a three-component reaction or two-step metabolic transformation that we're trying to analyze via a similar method. So we have from our chemistry and other science development, we have equations for how the amount of A, B, and C in this reactor change over time. And now I want to use this setup to figure out what's going to happen to this equation. What's it going to go to? Is it going to get to some sort of steady state? Is it going to eventually, get all to C? How quickly will it get all to C? Those are things I can all try to figure out using this model. So with something like this, you could sort of predict how long will it take to get to a certain concentration using a numerical model. Or you could take this the other way around and say you actually have data on these kinetics and what this reaction does. You can try to figure out what the parameters should be to fit that data. Using similar to what you do for a first order equation, you can do the same thing here where you're trying to best fit these parameters to the data. Again, we probably have to use numerics to do this part, but we can sort of analyze and see how it's going to behave just based on the behavior here. We also be able to get some information about like a steady state solution, something like that, just by looking at these equations before we go to the numerical model to see what's actually going to happen. And finally, we have an example that's going to come back a lot later this semester in another MATLAB assignment is the idea of disease spread. So this setup, we have n people in a population. We have people who can get the disease as S or susceptible, people who have it are I or infectious or infected, and people who have recovered are R. We then know the total population's N is S plus I plus R because everyone's one of these three categories. And we can come up with a set of equations that look like this for how this group is going to behave over time. Right, the susceptible people decrease when someone gets infected by interacting with an infectious person. The infectious people go up when someone becomes infected, but are decreased when someone actually recovers from the disease, and this grows with the recovery rate. And so with this, you can then answer questions like, given here, if I introduce one infected individual in a population of 1,000, how long will it take for the epidemic to reach its peak? When will I reach its maximum, as it's saying? What is that maximum, and then what's the steady state of this population? In this case, the steady state is not good, it means everyone gets it. But you can introduce more complicated things we'll do in the MATLAB to discuss how this behaves and what you can do to change this. And if you look at this, you'll see pretty standard graphs like you'd expect now that we are coming out of a pandemic of our own right. You'll see graphs look like what you would see in the news, right? You have a graph that peaks and then sort of tapers off like that. For the infectious rate, it's the exact same thing you would see, and you see this coming out of these equations as well. You can use these to model disease spread, and people have actually used these equations to model what's been going on with more recent pandemics, recent diseases, and see what sorts of actions being taken could affect the overall outcome of this process. Because if you have a more complicated model, you can tweak parameters and say how adding a certain restriction or a certain preventative measure changes a certain constant. You can then add that in to understand how it's going to affect the model and the long-term progression of this disease. There's three examples of systems mainly to illustrate how natural these things arise in science and engineering context. They come up all the time. It's very common that not just one thing is changing. So systems are very frequent, and being able to look at them, understand what they're trying to say, and analyze them, and view their results are going to be very important things as you move forward to apply this information in your future classes.